6 or 7. Depends on.
And then when the video.
Greetings and welcome, friends. We've been talking about geometric vectors on page 491. It's been a while. I feel a little rusty. In fact, my throat is somewhat sore as well, but that's fine. We're taking a look at question 2021, 21, and it says vector u minus r. So, by the way, the little symbol for vector is called a harpoon. It's not a full arrow. Full arrow would look like that. That would be like a ray or something like that, but it's a little harpoon thing. So if I want to do vector u minus r, now I'm just going to draw a picture of what this would look like, since I'm not going to do this to scale per se. But here's vector u, and we're going to do like the tip to tail method. So here's vector u, and that's at 340 degree angles this way, or 20 degrees that way if you think about it. And this is roughly 3.0 centimeters. Now if I want to subtract vector r from that, all right, subtract vector r. Man, repeating myself. That's so Khan Academy. Ugh. So anyways, so here's vector r. To subtract vector r, we're going to, in fact, add the opposite of it. All right, so it'll just be kind of in the opposite direction there, so to speak, or 180 degrees apart from it. In order to figure that out, I'm going to go from the tip here and kind of mark a new horizontal for me to work off of. And instead of 128 degrees, I'm going to add like 180 to that. So what am I looking at? Is that 308 degrees roughly, right? Something like that. So, so I would end up doing this 2.6 centimeters this way. All right. And now if I'm looking for the resultant of this effect, I would be interested in the vector that traveled from the beginning all the way to the end in one motion.
Now, why do you put R on the bottom of U and not at the same start point?
Like here for R?
Yeah, why does it not come from there?
You could if you were doing the parallelogram method, I think. And then that would work out. I was using the triangle method, which is like tip to tail, where I just keep adding them from one to the next like that. So my new vector u minus r, its angle I would measure from this horizontal, so I'd have to measure that anew. Okay, so I'm assuming that it's somewhat less than the 20 degrees. Technically, I could calculate it based off of these other angles if I use some like law of cosine work, as well as finding this dimension here. But you would have measured that with your protractor, but I expect that it's greater than 270 degrees. In fact, it's 324 degrees is what that ends up being. Somewhere around there, if you were within that ballpark, you're good. And the length of this resultant vector was 5.5 centimeters. Now, is the length just equal to the sum of these two guys? No. And in fact, I didn't expect it to be because they formed a triangle, so it actually had to be less than the sum using kind of triangle sum inequality relationships. So that's the idea, is you would just remeasure it off that horizontal. So let's take a look at the last problem here we're going to do. It says find the magnitude of the horizontal and vertical components of each vector shown for exercises 14 to 17. So it's looking for... I want to break vector r up into its horizontal and vertical components. So here's vector r. So its horizontal component would be a horizontal vector that would be one of the two vectors, one of the components that together, when added, would result in vector r. So there's my horizontal component. Here's my vertical component, something like this. So I might even call this... one might call this like r sub y vector, maybe. That might be a cool name for it. You could also call it Tony. This would be like r sub x vector, right, for the horizontal component. X and y seem appropriate. So really you could just draw those, and then you have to figure out, let's see, what's it say, the magnitude of each. So we actually could do this algebraically, but we're doing that later on in today's lesson. So yeah, you would just kind of try to measure this after you drew those accordingly with your protractor. So you would have just measured those distances. So for question 31, this r sub x, the magnitude of vector r sub x, which by the way, the notation for vectors is just excellent because there's like little harpoons, there's subscripts, there's absolute value bars, just to talk about a distance. It's quite wonderful. This should be equal to about 1.60 centimeters. Negative merely because it's traveling in kind of like this lefter direction there, so to speak. And then the other one is 2.05 for the magnitude of the vertical component.
Why did you measure that?
Vernier calipers, who knows, lasers. Maybe they shrunk themselves down to the size of like a centimeter and like went onto this book page and measured it. Like, who knows?
So if you just had two, that you get enough, right?
Yeah, I would also have accepted 2-ish.
So how did we get it so it's actually like closer to right?
That's just measurement. You could be off by probably like 10%. I'd still count it okay, something like that, so don't worry. But yeah, so actually just to foreshadow what we're doing today, if this is 128 degrees, what's this angle? 180 minus 128,
Like 52.
so 52 degrees. And if this is 2.6 centimeters, I could then find Ry and Rx using some like sine and cosine stuff if I wanted. So I could have actually said that, for instance, cosine of 52 degrees would equal the magnitude of vector Rx divided by 2.6 because it's adjacent to the hypotenuse. Oh, what? Well, we know this is 90 degrees, yeah. But the 52 is what I'd base it off of. And then you could also similarly set up the other one. So sine of 52 degrees is equal to the magnitude of vector Ry, the vertical component, divided by 2.6. And if you solve for each of those magnitudes, you'd actually get a really good approximation. I wonder if that's actually where they got that 2.05 that close. Although, maybe not. They probably tried to measure it. So anyways, thanks for watching, Internet friends. Tienen un día más bien del mundo. It's good to be back.